Alright guys, we're going to look at double integrals and polar coordinates in this next section. So let me show you a picture of why do we even bother with this. So let's say that we got an integral, a very straightforward problem. Find the volume of the solid. It's bounded by this paraboloid, okay, and the xy plane. So if you look at the xy plane and that paraboloid, they intersect when z equals 0. That's the xy plane. So we end up with the equation x squared, move that over to join the 0. You get x squared plus y squared equals 9, which is just a circle of radius 3. So all of this stuff, all of the points that get plotted into this thing live above, in between that circle and the xy plane. The x and y coordinates all live in between the circle, and all the points get plotted up out of the xy plane over that circle. And then we have the boundary where we intersect along the xy plane. So if I wanted to graph this, set this up, this integration, I would have to pick one. Who do I want to be on the outside? So let's just say, I want the x's to be on the outside. And so my x's go from -3 here to +3. And along those values for x, as I'm making my way along that path, what's happening with y? So again, if I just pick a random value for x in here, let's say this value, how are the y's changing? Well, up above, the highest value of y is up here on this part of the semicircle, and the lowest value of y is down here on this part of the semicircle. The equation of that circle is y equals, on the upper end, the positive square root of 9 minus x squared. And on the bottom end, it's y equals the negative square root of that, 9 minus x squared. So these are the values that y are ranging between along there for any given x. So you give me an x. How do I find the y coordinates that it's bounded by? I plug them into these two equations, and that gives me my lower and upper bound for y. So these are going to be the limits of integration for the y part. And then I've got the integrand, which is 9 minus x squared minus y squared, and then my differentials. So I'm doing y first, and then x is on the outside. Alright, so if you look at what we're going to get, when we do that integration, we're going to get the 9 minus x squared is going to get a y to it. Both of those terms get a y, so I'll just, 9y minus x squared times y. I'm just factoring the y out. And then the y squared part gets a y cubed over 3. Now, what are we going to do to that? Think about this. We are going to have to distribute this in for every y. So 9 minus x squared times the square root of 9 minus x squared. Well, that's not bad. That's 9 minus x squared to the 3 halves. And then subtract when we plug in this part, the negative 9 minus x squared. Right, now we're subtracting because of the integration, but it's negative, so we're going to end up adding. So we're going to end up with 2 of those 9 minus x squared to the 3 halves. And then the same thing's going to happen here. We plug in this to the, we plug this into the 3 halves. We're going to get another 9 minus x squared, that's to the 1 half, to the third, so that'll be the 3 halves, over 3. And then we're plugging this in. This is negative. This negative that goes in will make it this negative times negative is a positive, but we're subtracting, so once again we're going to get more negative. But the thing is, everything's going to have this 3 halves power of 9 minus x squared. All the terms are. Now we can combine them and into a nice compact form. There's going to be a lot of simplification since both pieces will have a 9 minus x to the 3 halves power. But still, it's a radical with x squared underneath it with no x on the outside. It's not going to be a substitution. You're going to have to do trig substitution to solve this, which is, it's not, of all the integration techniques you learn in Calculus 2, trig substitution is not the worst. It's just tedious. It's a tedious process, and it's going to happen virtually every time that we have these circular regions in our integration, elliptical or circular, you're going to have these radicals involved. So bring in polar coordinates. What does polar coordinates do to a problem like this? Well, if we switch these things from the rectangular coordinates to the polar coordinates, what we have to do, it's not just a straightforward switch, and this gets into it. You can look through your PowerPoints that I posted, that we cut up the grid, and when we cut up the grid we get these little wedge shapes. And if you look, every single one of these little wedge shapes here they're made up of, let me zoom in again, these aren't rectangles, these are like these little pieces of a sector of a circle. So because they're not rectangles, it's not exactly rectangular that we're seeing. It is operations with sectors of circles. And so what these slides are going through is to giving you the idea, how do we find what the areas of these things are. But it comes up with, if you just come up with one little wedge, the area of this one little wedge is r, like the current radius that we're on, all right, our polar coordinate. And then this dr is the change in the radius. So if we were here and we went to here, so we're dividing up the region into those rectangular, or these we're making a grid in our region. So from one to the next, that's one value of r, that's another value of r. Well, that change, that uniform change that we have is the delta r that it's talking about right here. And then delta theta is the change from one of these to the next. So if we change theta from this angle to this angle, that's delta theta, and then this angle to this angle. So in that picture, we end up with a value that falls between these two thetas and these two r's. Okay, so it's just the average of those two r's, and we're plugging it in like right in between the middle of this theta. And that represents one of these regions. But what the point of this is, what we want you to see is, it's not like before. If it was rectangular, it would be dx dy. It's not just dx dy. Our new, polar coordinates are r and theta. So we get a delta r and a delta theta, but we also get this extra r when we do this procedure, because the area of one of these are based on the areas of sectors of circles, and this is the formula for a sector of a circle. So this is like the outer sector at Ri, this is the inner sector at Ri minus 1, and so this region right here, this area, is given by this formula. So it's because it's not rectangular, we're getting this extra little piece here. So the point being, when we switch from rectangular to polar, if we switch our arguments from x and y to r and theta, we have to remember this extra little r, dr d theta. Okay, we got to switch from x and y to r and theta, but we have to stick in this extra little r here. Alright, so back to this guy. So we saw that this was getting ugly pretty fast. So what's going to happen in polar coordinates? Well, in polar coordinates, this base, this circular base, is just the equation r equals 3. Alright, this is theta equals 0, and then if we go all the way around to cut out the whole circle, we're going from theta equals 2 pi. Okay. The other thing we got to get down is our integral. Our integral was 9 minus x squared minus y squared. Well, remember, r squared is x squared plus y squared. 'So, that means that negative r squared is negative x squared minus y squared. So what does that mean? That means that I can write our new equation as z equals 9 minus r squared. Okay. And now our integral, watch this, this is how much easier this is going to be in polar, is our integrand was 9 minus x squared minus y squared, where in polar that's going to become 9 minus r squared. Alright, now because I'm switching it to polar, I need to add an extra r dr d theta. Sometimes we call this pirate math. R dr d theta. Alright, and then dr, that's my innermost differential, so that means this innermost integration symbol, it deals with r. What does r go between? It goes between 0 and 3. Our radius is going to get all the points in the middle of this circle. That's our serving as our base. Our radius would have to go between 0 and 3. And then what is theta going between? It's going between 0 and 2 pi. And that becomes a much nicer integral to do. Okay? Much, much nicer. I distribute the r through, I'd get 9r minus r cubed. Alright, the antiderivative of 9r is going to be 9r squared over 2. This is going to be r to the 4th over 4. Alright, and then I plug in a 3 for both of these. I'm going to get 9r squared. Alright, r is 3. So that's 9 times 9, that's 81 halves. Minus r to the 4th, which is 3 to the 4th, is 81 fourths. So 81 halves minus 81 fourths is 81 fourths. Alright, and then there's this constant, there is no theta here, so when I integrate, I'm just going to get a theta times this, and because the bottom one is 0, I just end up multiplying by this. So I'm going to end up with 81 fourths times 2 pi. Alright, the pi, the 2 and the 4 were reduced to 2, and so I end up with 81 pi over 2. That's the volume here, and that's what we would have gotten in the other method if we would have continued on with the trig substitution and everything. But I ended up with nice clean numbers here. I didn't need to do trig substitution. I just ended up with basic power rule and constants. So it made it a much easier integration to do. Alright, here's another example. And this one, unfortunately, if I try to do this with rectangular region, R is the unit disk. So again, that's just the circle centered at the origin, but all points between that as well, is our region in the xy plane. So it's just the unit circle with all the points between it. So we're told to evaluate that. Well, unfortunately, this guy doesn't have an antiderivative. Because we got x squared and y squared in there. It doesn't have an antiderivative in closed form with either direction if we did with rectangular coordinates, x or y. But once again, you can tell because I got the unit circle, I'm going from, -1 to 1 in either direction is my outer region, and in between there I'm going to have square roots because it's circular. No matter which way I pick. If I picked, y to be the outermost and went from -1 to 1 in y, well, how do I get to my x's for that y? It's negative square root, positive square root. There's going to be radicals involved. It's going to be an ugly thing to do. But if I switch this to polar, this becomes r squared, right? And we need to stick an extra r on there, so r dr d theta, and our limits integration in terms of r and theta are going to be, again, r is going to go from 0 to 1, and theta is going to go from 0 to 2 pi again. All right, we don't always have to go to 2 pi. It depends on what the shape looks like. But when it's a full circle like this, we do. But here's the nice thing. This is now e to the r squared r. So we have an r squared and an r. So what can we do? We can do u substitution on this thing now, where we didn't have that extra x or that extra y before when we were trying to set it up with rectangular. The r, because of the necessity, because of integrating in polar, you have to have that extra r. So that r squared gets its derivative, or a scalar multiple of its derivative, to be able to do u substitution. Alright, so we switch it to polar. We get that, like we said before. Do a nice little u substitution. U is negative r squared. du is negative 2dr. So I need to have this extra 1/2 because I need to force this to be there. And now this is just straight up basic integration. Alright, the antiderivative of u with respect to e to the u with respect to u is e to the u. So we plug in negative 1, we get e to the negative 1. Minus, we plug in 0, e to the 0 is 1. Alright, and then we integrate with respect to pi, just like we saw before. Because that's a 0, this is all constant. We end up just multiplying by 2 pi. And then just distributing through and simplifying, we end up with pi. These two things cancel. And then notice I'm just changing the order around the minus sign because of the negative out here. Distributing it through, the 1 becomes positive. The e to the negative 1, which is 1 over e, becomes negative. Gets a negative in front of it, so 1 over e. And the 1/2 of the 2 cancel. So that's where that's coming from. But this becomes from one we can't do at all in rectangular to one that we can do fairly easily with just a basic u substitution in polar. So again, we can go from our first example, it goes from difficult to simple, and then it goes from, with these later examples, impossible to relatively easy. It wasn't, we still had to do u substitution, but of all the trig techniques that we got in calculus 1 and 2, that was probably the most basic, easiest one. Alright, so there are your switching it to polar. We're going to go beyond that as well. We're going to do something called cylindrical and spherical coordinates coming up, which have a little bit to do with polar. And one of them basically is polar with z, is cylindrical coordinates. And then spherical has polar as part of it. We also introduce another angle. And it takes us into the polar or the 3D version of what polar coordinates are.